serial communication, embedded serial communication protocols are very important also for IoT, because you have some elements on the boards during labs that are connected with such protocols. So we can say the same topic for two subjects. Okay, so we start. Hello, today serial communication in IoT, we can call it embedded protocols, because these protocols connect microcontroller and some peripheral elements that are external to the chip. And we can say we will talk about serial ports, and the serial ports can be asynchronous and synchronous, depending on the way of communication, way of implementation of this communication. Asynchronous communication and synchronous communication is very popular in embedded systems and in IoT. Asynchronous ports are like UART, like one wire, and like CAN communication. And I think the most popular is UART, and you use it quite often, because UART is the main communication protocol between microcontroller and the USB conversion chip. If you find almost any IoT microcontroller like ESP8266, ESP32 or some others, there is a special chip on the board that converts USB to serial port, and the connection from the microcontroller's point of view, there is a serial port. And also, if you take the PC computer and check what is the communication port for controlling, for reflashing, and for communication with microcontroller, it also will be virtual COM port. So this is also serial port. So serial communication is quite important. This is asynchronous communication, and we will talk about it in details. One wire is also a very nice protocol that uses just one single wire. Of course, there's also the ground connection required, but using one wire you can connect some elements. And we have also synchronous communication. Asynchronous communication, also very popular. We have two main protocols. One is called SPI, Serial Peripheral Interconnect, and second is called I2C or TWI. TWI comes from two-wire interface, I2C from integrated circuit. This I2C was created by Philips many years ago, and the name, the protocol itself not, but the name is restricted. That's why a lot of other producers use the name TWI. Sometimes, especially in microcontrollers, we have the unit that is named UART, and UART is the connection of two possibilities: asynchronous and synchronous communication. That's why this is USART, but not UART. Okay, so for UART, UART comes or stays for Universal Asynchronous Receiver Transmitter. It's the unit that is implemented normally inside every microcontroller. In a history, in PC computers it was separate chip. Now everything is miniaturized, so everything can fit into one small part of silicon. And the main principle of UART is that there is no separate synchronization signal. The synchronization is included in the data frame somehow. What is important here, the timing is very strict. So we must specify what is the, for example, duration of the beat, of the single beat in the transmitter, and it must correspond to the receiver. In such situation, it is possible to synchronize receiver and transmitter and to receive this data. Data is normally sent in frames. There must be some rules how to start the frame, how to finish the frame. Of course, not only in UART, but in UART this is especially important. As I said, it is possible that one unit connects two modes of communication, asynchronous and synchronous. Of course, they cannot be used at the same time, but the module can support both protocols. As we said, in UART, the communication speed, sometimes called baud rate, but this is not, I think, proper. I learned about it, that this is not proper naming, because this is baud is the symbol per second, not bit per second. We should say bit per second, or BPS for UART communication. So it differs between 300 BPS. This is very small, very low communication rate, but sometimes it's enough, up to 115,200 bits per second, and these are standard speeds that you can find supported by many microcontrollers. Modern microcontrollers also support higher speeds, up to 3 megabits per second. And what is important in UART, that UART provides point-to-point communication. So notice, like in this picture here, we have TXD line, so this is transmitter output from one unit. It is connected to receiver input in another unit, and the same as in opposite direction. So this is quite important. You cannot connect TXD with TXD, because you will connect two outputs together, yeah? And for sure communication will not operate properly. This is slightly different than in other connections. Usually the connection between different chips has the same name, and we can connect all connections or pins with the same name together. Here not. Here you need to observe it. And even I have found devices that shows the name, for example, on the board, on the module, from microcontroller's point of view. So in such situation, you connect TXD with TXD. So you need to please always refer to the documentation, how it is connected, and which pin should be connected with which. As we said, UART communication goes in frames. And here is the picture that shows such frame. The frame always begins with the start bit. Start bit is always 0 in or logical 0. I'm not talking about 0 voltage, because it depends on the hardware implementation of UART. But start bit has always value of 0, logical value 0. Next we have bits of data. Depends on the construction, from 5 up to 8 bits of data. This is configurable. Of course, our computers now, modern computers, usually work with data that is organized in bytes. Byte, it is assumed that that byte has 8 bits, so usually the UART sends 8-bit data packets. After this, we can have parity that can be even, can be odd, can be empty, and even cannot appear at all. It depends on our need. Normally, for example, if you connect your microcontroller, your IoT node to computer for reflashing or for something, usually there is no parity at all. So this bit is not present. And after this we have stop bit that is always opposite value as start bit, so 1. The stop bit can last at least 1 bit. It can be 1.5, it can be 2 bits in length, of course, but it can be longer, because the stop bit has the same value as idle channel. So if there is no communication at all, the idle channel has the same value as stop bit. After at least single stop bit, we can start another start bit and further communication. And notice what happens here. If we have stop 1 and start 0, there is always this transition, yeah, between stop and start, and this transition synchronizes receiver and transmitter. So at least two transitions must be here, yes, at least one between stop and start, and somewhere here also must be another transition. Because if we send, for example, byte equal to 8 zeros, it will be start bit 0 and the whole signal remains 0 whole the frame. So only stop bit will be 1. So sometimes in hard situations it is quite hard to distinguish, for example, if we send single bit of 1 somewhere in between, it is hard to distinguish if it is stop bit or if it's informational bit, yeah. But it is responsibility of the UART unit inside the microcontroller and inside PC computer to recognize it. A simple schematic diagram of such UART can be like this. We have clock generator that normally generates the same frequency to synchronize receiver and transmitter. We have shift register that sends the information out, and also shift register that accepts information coming from external unit. And we have also additional registers, we can say such temporal registers, that stores the data to be sent and stores the data that has been already received to be able to receive another byte. Sometimes it represents not single register but short queue of data. Very popular implementation of UART is named RS-232. Maybe it's not so popular now in PC computers, but it is still quite popular in industry. And RS-232 operates with UART frames, so we can say this is almost the same, but with different voltage levels. RS-232 operates with voltage levels, we can say, in a negative logic. So there is a special converter needed to convert between the normal logic that is exposed on the pins of microcontroller, for example, because on the pins of the microcontrollers, 0 state is 0 voltage. High state is, or 1 state is close to power supply. In RS-232, voltages are reversed. I'll show you in next slide how it works. Of course, connection is the same. We have RxD and TXD lines, and here is the slide that presents the voltage levels. So transmitter, if it sends 0, it can send voltage from 5 up to 15 volts. Notice 0 and high voltage. While we have 1 state, we send from -5 up to -15. So this is reverse logic, and additionally we have negative voltage here. And receiver accepts a little bit wider voltage ranges, so it is possible to accept, for example, voltages from 3 volts up and from -3 volts down. So, as I said, special chip is needed, and such chips are produced, and they normally not only convert this, but they also are able to generate this negative voltage, because normally you don't have negative voltage in your circuit. Normally you have the power supply, ground, some +5 or +12 voltage, and here you need to generate something that is minus. So this minus is generated automatically in these chips. This is view of the RS-232 plug. As I said, now it's not popular in PC computers, but in industrial computers it is. These 9 pins can connect not only TXD, RxD and the ground, but also some control signals, because at the beginning this UART connection was used to connect modems. And we need to have some additional information to establish communication with the remote modem. For example, detect if there is a signal on the telephone line, detect if we could establish connection, detect if the remote modem is operating properly. So additional signals were here needed. And the description of the signals is like this. Of course, RxD, TXD are the data lines for receiving and for sending data. DTR is the data terminal ready, is the information from computer to modem that computer is ready to accept data. DSR from modem to computer that the modem is ready. RTS, CTS are synchronization signals that device wants to send the frame and the other device accepts the frame sending. Ring indicator is the information that we have incoming call, and DCD is the information that on the signal coming from telephone line we have carrier from modem. This is a schematic diagram of the conversion chip that allows us to connect RS-232, for example, from computer, to our microcontroller from the side. This chip is named MAX232 or 202, depending on the construction. We have different capacitors here. For example, in this MAX232, we need to have 100 nanofarads capacitors, so they can be quite small. And using these capacitors, this chip automatically generates, this is something like voltage pump, and it generates this negative voltage. So as you can see, it's quite simple. One small chip, few capacitors, and we have connection to RS-232. And another chip I wanted to show you, this is converter from USB to UART, and this is what we have on our boards in IoT for programming, for example. Yeah, we can connect USB to computer, and of course USB works with 5 volts, but the protocol is completely different. So we need the converter between USB and and UART, not RS-232 and UART. So we have special chip that here connects USB with all the requirements of USB, with all the presentation of the chip, so our operating system can recognize it and recognizes it as virtual COM port. And this virtual COM port is exposed here as these TXD and RXD lines. And if you look at this picture, we also have all these lines that are normally connected to the modem. So this chip not only allows us to connect our simple microcontroller, but also normal modem we can connect here, or plug to the modem we can connect here. Notice that here we have this DTR line, so data transmitter ready. We have also possibility to reset our microcontroller with this signal. So if we have software that can use this possibility, it also can reset our microcontroller, for example, after reflashing. So this is everything about UART. Now we go to first synchronous data communication protocol named SPI, Serial Peripheral Interface. So this is a connection between one device that is primary device and other devices that normally are not so smart as microcontroller, we can say. So this connection, SPI, is used to connect microcontroller and some other devices like EEPROMs, like data flash memories, like SD cards, like the converters, analog digital converters, for example, real-time clocks, some other units like web LAN, so network controllers, some sensors, displays, graphical displays even. And in some situations this protocol is used to connect programmer, so some programming unit. If there is, for example, no possibility to connect or to reflash our microcontroller through serial port, usually we have something that is named in-system programming, and this in-system programming usually uses SPI as the main protocol for data communication. We have 4 lines that connects our primary device and secondary devices. and most signals are generated by primary devices. So we have clock line. This clock line that didn't appear in UART here appears and synchronizes the communication. So all the communication is clocked with this SCK signal. We have two data lines: master input, slave output. So this is data that comes from secondary device to primary device, and the other master output slave input, MOSI, that sends data from primary device to secondary device. And the connection of SPI looks like this, that all SCK lines of all chips, so microcontroller and for example many devices, many secondary devices, are connected together. In such situation, we must be able to distinguish or to activate only one of the chips that we want to perform connection with. So we have special line that is named slave select or chip select or module select, and this line is separate or separately generated from microcontroller to every chip. So only one secondary chip at a time can be activated. And in such situation we perform communication between microcontroller and this one activated chip on the bus. Clock is always generated by master device, and every secondary has separate slave select or chip select signal. So yeah, this is what I already told, that we have these lines are common, so they form something like bus. Yeah, and in the bus connection, there is always requirement to activate just single element. So the implementation can look like this. Here we have microcontroller. We have all these three lines connected together, so clock line generated by microcontroller to all secondary devices, master output slave input the same direction from microcontroller to all secondary devices, and master input slave output connected together from all secondary devices to one primary device, and separate lines to activate first device, this green one, the blue one, and the purple one. Yeah, depends on the need of communication at specified time. Block schematic of the SPI implementation inside chips can look like this. We have clock generator in the primary device. This clock synchronizes both shift registers, and the data that goes out of primary device comes as the input to secondary device, and at the same time data that comes from secondary device can be shifted into the register of primary device. So the communication in both directions occurs at the same time with the same signal. And of course here we have generator of this chip select signal that activates our slave device. It is much simpler than UART, because in UART we must find the beginning of the frame. We must normally in UART every bit is sampled at least 3 times, sometimes even more, to distinguish if this is really 0 or is it really 1, if this is start bit or not. Here this implementation is much more simpler of the SPI. That's why it is possible to connect to SPI bus very simple devices like shift registers, and they should operate. SPI works in 4 different modes. These modes are not very different in implementation, but they are controlled with 2 bits. In some implementations they are named control of the polarity and control of the phase. And here is picture that shows how these modes of operation work. In mode 0, as you can see, this shapes here represent the data line, and here we have clock line. And in mode 0, the data is locked in the, or latched in the receiver in the rising edge of the clock signal and at the beginning phase. Here we have, in mode 3, we have also rising edge of the clock signal, but this is the finite phase. This is beginning of the phase, this is finish of the phase. In mode 1 and 2, we have falling edge, but in mode 2, the first slope, in the mode 1, the second slope. Yeah, so these are the difference between this mode. So not every device supports all the modes. You need to refer to documentation. Microcontrollers usually can communicate with any mode, just you need to configure it. Example of the connection of SPI. Here we have some microcontroller. Some microcontrollers have this possibility implemented, so have unit for SPI. Sometimes this is even the same units as for UART. Yes, we have UARTs that can operate like UART, but sometimes like SPI. So here we have the names of the lines as they appear in the we can say de facto standard or industry standard, and here we have the chip. This chip is data flash memory that can be connected using this SPI, and because we just have one such chip here, we don't need to generate additional chip select signals. But of course, if we need to generate some additional chip select signals, we can do it using normal port outputs. So because normally internal unit normally generates just single such signal, but if we need additional signals, we can use normal input outputs of ports and just set it or clear it and control the communication. There is also some additional extensions of SPI, for example, quad mode of communication. Quad SPI means that we have 4 data lines. We have also double data lines, quad data lines. Of course, if we have 4 data lines, the communication can go faster because we transmit 4 bits at the same time. And in this situation, we have lines named not MISO, but IO1 up to IO3, up to IO4, and they communicate just half of the byte. Yeah, so one half of the byte and next second half of the byte, and so on, so on. Of course, to be able, because notice that there is no the lines are one directional at the moment, so first we need to somehow choose the communication mode, reading or writing, and after this send the data. So this mode of operation requires sending some commands at the beginning, setting the mode of operation, and after this we can receive the data. Example of such quad SPI. I'm pretty sure that you heard already about ESP8266, and you will see these chips during our laboratories. And this chip, ESP8266, has the external flash memory that is connected using QSPI on the same board. Yeah? So we have 2 chips on the board. One is microcontroller, second is flash memory that contains the program, and it is connected using this QSPI protocol. Another protocol that we use to connect some external elements, sensors, actuators to our IoT microcontroller is TWI. TWI stays for two-wire interface, and it is also sometimes named I2C. The name has been developed, and the protocol has been developed by Philips. I2C means inter-integrated circuit, and the name is restricted by Philips. That's why other companies usually name it two-wire interface. It allows us to connect a variety of external elements like EEPROM memories, analog to digital and digital to analog converters, real-time clocks, port expanders, so similar devices like SPI, but the main difference between SPI and TWI is the method of activating the secondary device. all the devices in TWI are connected using two lines, SDA, so this is data line, common for all the devices in the bus, and also SCL, this is clock line. Clock line is always controlled by the primary device. Data line is controlled by both primary or secondary, depending on the direction of the communication. Both lines need pull-up resistors to ensure that we have one state if no data is sent by primary or any secondary. Every output of this unit inside microcontroller and other devices is implemented as transistor with open drain. So there must be external pull-up resistor, like here on the schematic diagram. Here we have these two resistors connected to the power supply that ensures that we have idle state one on both lines of the bus. They are sometimes called terminating resistors. Sometimes they are implemented in the devices. We can, for example, activate pull-up resistor in microcontroller, and sometimes it is quite enough to ensure that our bus work properly. This slide presents the frame of the TWI protocol. So here everything starts, all the communication starts with something that is called start condition. The start condition is falling edge on SDA line while clock is 1. After this, the physical address of the device is sent. This physical device consists of 4 parts. I will explain them in the moment. Here's device ID, here is the physical address of the chip, and the last bit decides of the further direction of communication. If it's 0, we write something to the secondary device. If it's 1, we read something from secondary device. Properly addressed secondary device must answer with acknowledge here. So on the 9 bit, on the 9 pulse, we have the response from the secondary device. Okay, I am here, I am active, and I can work with you. And after this, we have another byte that is normal byte of communication. It also must be acknowledged, and always receiving element acknowledges. So if here we read data from secondary device, primary device must acknowledge the communication. Everything stops with stop condition, that is rising edge of the data line while the clock is 1. Let us assume that we have the memory and we want to write the data at the address, for example, 10. So first, we need to address physically the chip on the bus, so send the physical address. After this, we need to send the address of the byte that we want to access. So the second byte will be, for example, 10. This will be the address of the device, and the third byte will be the content of this byte in the memory that we want to write. So to write the data, write single byte into the memory chip, we need 3 bytes of communication. If we want to read the data, it's even worse, because we need to address the chip for writing, write the address of the byte that we want to access. Next, we need to restart the communication, so we need to send this address byte again, this physical address again, with 1 here, because we want to read something, and after this we will be able to read single byte from the memory chip. So 4 bytes of communication to read single byte. So as you can see, the TWI communication has quite big protocol overhead, and that's why it is rather used for sending and receiving small amounts of data, like simple measurements, I don't know, of some temperature, humidity or something. So up to few dozens of bytes. This is all that we can normally achieve using this TWI communication. Example of the chip that is connected using TWI. This is a real-time clock chip. with the possibility to connect the battery, and just 2 lines SDI and SCL, and everything is done, of course, as the logic in the chip. All the implementation of the protocol is inside the chip and inside the microcontroller. Very large amount of microcontrollers have implemented also this method of communication as the special unit. Sometimes we need to write some part of the software to implement it, we can say from scratch, bit by bit. It is also possible. Few words about addressing, because I told you that this address byte consists of 3 elements. One element is, or 4 bits are defined always for the specific device. Of course, we have just 16 possibilities here, so for sure there are many chips that have the same pattern of bits, but sometimes not. Sometimes they have different. And for example, such series of EEPROM memories, 24C02 up to 16, and they have 256 bytes up to 2 kilobytes. Oh, you can say that this is not a large amount of memory, but sometimes, to store the configuration is enough. They implement such method of addressing that 4 bits are fixed in the chip, we cannot change it. Next 3 bits for this 2 kilo version, notice that here we have 3 lines, A0, A1 and A2. And if we connect all these 3 lines to the ground, we need to send here 3 zeros to access this chip. If we connect, for example, A0 to 1, we need to send 0, 0, 1. So it allows us to connect up to 8 the same chips on the same bus. We can distinguish them. Of course, every chip must have different connection of this A0 up to A2 lines to the ground and to the power supply, but we can address them as separate chips. But we don't have more these lines, but for example, to access 2 kilo words, we need to have additional 3 lines of internal address of the cell in the memory. That's why this 3, 2 or 1 bit from address is intended to address internal page, we can say, yes, because normal page has 256 bytes. It is addressed using the first byte sent after this address byte, but if we have twice amount of memory, we need additional bit. So this bit is here. It chooses the page 0 or page 1. The same here we have 4 pages, here we have 8 pages, so we have 2 kilobytes of memory. Another chip that is quite popular is something that is called port expander. Port expander is the chip also connected using our I2C lines. It also has 3 lines for addressing, for distinguishing between 8 such elements. And here we have 8 lines of the ports that are bidirectional. So we can treat them as input or as output. This chip is used in converters that allows us to connect LCD display to microcontroller through I2C connection. So we have normal display, LCD display, to 2 lines, 16 characters, and there is such chip that makes this conversion. Of course, we need a special library to be able to display something, but it is possible to do it. In the laboratory, we use the 4-bit direct connection, but you can find on the market such displays that are connected through I2C. So exactly this chip is used to make this conversion. And additionally, we have 2 versions of such chip. One is without A and second is with A. They differ with this 4-bit pattern. Without A, we have pattern 0100, and with A, we have 0111. So we can connect up to 16 chips on the same bus. Of course, 8 must be with A, 8 must be without A. Yes, so we can distinguish with 16 similar chips on the single bus. Of course, if you want more, we need to create another bus, yeah? another 2 lines and another I2C bus. Another popular communication, serial communication, is one wire. One wire, you can even have less connection lines than I2C because it needs just the ground and one line that allows us to send both power supply to the secondary device and also it can be used for the sending data. All these devices implement the internal capacitor that stores the charge that is enough for powering this internal device while there is no power supply on the line, while sending 0, yes, or sending 0 pulses. They implement such capacitor and they have enough charge to power it. The data rate is not so high because this is only 16 kilobits per second, so this is even slower than I2C. And we can distinguish between different devices because they have unique 64-bit serial number. And the very popular chip presented here on this slide, this is a Dallas temperature measurement unit DS18B20. Yeah, this is very popular, and you can buy it very cheap and make some experiments with it. The schematic diagram of the connection using one wire is like this. We have here the primary device, many secondary devices we can connect. We need to have this pull-up resistor that allows us to power supply all these devices and also ensures that we have stable one state on the line. Normally, these devices allows us also to connect additional power supply line, but if we want to minimize the number of wires, we can even use such architecture. How the communication starts with the reset pulse. It has special timings, so we need to keep these timings if we want to communicate with one wire. So this reset pulse is 0 state for at least 480 microseconds, and after such state, secondary device should respond with the pulse from 60 up to 240 microseconds. And after this, we can communicate with this device. Of course, first we need to write something to be able to read. So this is signal from primary device, and first byte is sent most significant, the last bit is sent the least significant, and as you can see, the one state is represented by short 0 pulse and long 1 pulse, and 0 state opposite. Long 0 pulse and short 1 pulse. Synchronization here is achieved because every time we need these transitions between 0 and 1 twice, so the synchronization is quite easily to be achieved here. That's why we don't need the synchronization line, additional synchronization line. So we can say we have something like asynchronous communication synchronized with the information encoded in the data signal. The length of this one pulse is 15 microseconds, 0 is 60 microseconds. And read sequence looks like this. Primary device always generates such short pulses here, and secondary device, if it wants to send a 0 state, responses with or prolongs this short pulse with 0 for specific time. So 1 means there is no response from slave, and if it wants to send 0 state, secondary wants to send 0, it prolongs this pulse up to 60 microseconds. One wire is not so popular as SPI and and TWI, but it is. There are some different constructions, mainly by Dallas Semiconductors, because they designed this method of communication. There's quite popular humidity and temperature measurement unit that we have on our laboratory. It is named DHT11 or DHT22. They communicate with something similar to one wire, but this is not exactly the same. The similar protocol, but not the same. And another protocol, quite popular, maybe not in all embedded systems, but rather connected with automotive industry, is CAN protocol. CAN protocol is named for Controller Area Network. It has been designed especially for automotive industry, and with some requirements, with some assumptions they assumed to design this protocol. The assumptions were transmission speed from 5 kilobits per second, so for some control purposes, up to 1 megabits per second if we need to send more data. For example, if we need to send the parameters from the engine all the time, so hold the stream of parameters, so it requires more bandwidth. Requirement is that there are no transmission errors. Of course, this is not achievable, but if there is an error, we can detect it and we can somehow resolve the situation. It is optimized for small data packets, low cost of production and service, and low installation. So it means bus architecture is required, like in almost all protocols that we talked about today. CAN specifies 3 layers of the, we can say, networking: physical layer, data link layer, and above all these layers we have application layers. Layer 1 tells that CAN has bus topology, so all devices in one CAN bus are connected together. We have serial asynchronous communication, so something like UART. Physical media is twisted pair, so very cheap. We have twisted pair with shield, without shield, and what is needed here are termination resistors. We have 2 lines. They are named CAN-L and CAN-H, and the communication, to ensure the high reliability of communication and resistance on the electromagnetical distortions, we have differential communication. Differential communication is also implemented in some versions of UART, for example RS485. This is similar to RS232, but for industrial purposes, and different voltages we have there. And also we have twisted pair differential communication, like here. So if the voltage difference is lower than half volts, we have logic 1, and it is called recessive state. If the voltage difference is higher than 0.9 volts, it represents the 0 state, and it is called dominant state. This recessive state and dominant state work like this, that if 2 devices are sending at the same time one recessive state and second dominant, we can say dominant wins. So dominant has higher priority than recessive state. This is quite important on the construction of the access control of this protocol that I show you in the moment. The length of the cable can be different, even up to 1 kilometer. You can ask why 1 kilometer, but if you imagine how many wires we have in the car, it is a really long metal wires inside. And depending on the length of the wire, we can achieve different speed of communication, and we need to use different values of the terminating resistors. Medium access control layer, so this layer that enables different devices to access the medium is based on the protocol that is named CSMA-CD. This is Carrier Sense Multiple Access with Collision Detect. Next slide will show how it works, but the whole communication is based on the principle that we have this recessive and dominant state. Dominant state wins, and because we have wired communication, we can send something and we can check if it appeared on the line. So if we send the dominant state, we can check if it's present. If we send the recessive state, we can also check if it's present, measuring the voltage on the difference on the voltage during sending the information. The arbitration, rather the method of the access to the medium is based on this principle, and everything, hold the arbitration or hold the contention between stations is made at the initial stage of the communication with addressing field, and we can address using specific address of the device. So for example, station A sends some data to specific station B, or we have something like message addressing. So it means that station A sends the message to many stations that are interested in this value. For example, it addresses that, okay, I'm sending value X. And we can, for example, the controller of the car sends the message to all bulbs, I want you to switch on. Yes, because it's night, so I want you to switch on. So every bulb controller that is implemented at the beginning, at the front and the rear of the car, they receive the same message. And this picture shows how this arbitration works. Let us assume that we have three addresses here, address N1, N2, and N3, and they differ somewhere here. As we said, 1 is the recessive state, 0 is the dominant state, so 0 wins. So if here we have what 3 stations try to send. Of course, they must start sending at the same time, and this is one requirement of the CAN, that all the stations can start at the same time. So all the stations send 0, 1, 0, 1, 1, 0, and until this moment, every station sends this, and every station checking on the bus thinks, okay, everything's okay, yeah? I'm sending the same value that appears on the bus. But here, first difference appears. N3 wants to send 1, but other stations want to send 0. 0 is the dominant, so N3 loses here, we can say, yeah? So it stops further communication. Next, we have 1, 1, and again, 1, 0, and 1 sends 1, recessive state, N2 sends the dominant state, so N2 is the winner of this competition here, yeah? So this is the method of, we can say, arbitration. The message, some addresses have higher priority and some messages have higher priority than others. And this address decides about this priority. Layer 2 also defines the frames. We have special fields in the frame, so we have start bit, we have next identifier, so this address, we have some control field, data fields, check field, and acknowledge, and also some informational that the frame has ended, and at least 3 bits of idle state. These packets can have different types. We can have data frame that contains normal data. We can have remote frame, so we want to access the data from some other chip. We have error frame that propagates through the network to tell other devices that some error appeared and we need to restart the communication. And we have also overload frame to inject and delay if it's needed. Error detection is performed on a few different levels. One level is the detection of the bit sent and what is different, what we want to send, and what is different that we see on the bus. There is also called bit stuffing. This is quite often used technique to ensure the synchronization between the receiver and transmitter. If we send the 5 bits of the same, it's the 6 bit of the same value, we need to include between bit number 5 and 6 at least 1 bit of the opposite value. That ensures the synchronization between the receiver and the transmitter, and it also enables us to signal and propagate error. Because if we send 6 bits of the value 0, it means there is an error, we signal the error and propagate it through the network. There is also cyclic redundancy check that we can compare. There is also acknowledge error, so if we don't get the acknowledge, we know that the message didn't reach the destination. And we also have format error detection, so it means in the frame some bits have known value and they cannot be different. So we can, in such situation, we can check if the received frame is proper or not proper. While we detect the error, the receiving node tries to propagate error to another stations, generating 6 dominant bits on the bus. Because the 6 dominant bits breaks the rule of the bit stuffing, because there should appear at least 1 bit of 1. Other stations know, okay, there is an error on the bus, we reset the communication and we start everything again. And the last slide today is about the implementation of CAN protocol. There are implementations of this protocol as the hardware unit that is inside the microcontroller. You can find such microcontrollers on the market, but of course you can also have it as the separate chip, and you can connect this chip to the microcontroller with some other protocol like SPI or TWI, depends on the construction. And what is nice and what is interesting in this CAN, it is filtering. So it is possible to program our unit in such a way that we want to accept frames only with specific list of the devices, something like whitelist. Yeah? So we can accept frames only from specific chips. So it means only CAN unit can work, and it wakes us up, it wakes our processor up only while it's needed, and we have some data to be read. Okay, so this is all I wanted to tell you today about protocols. I think it will be useful while you implement some IoT connections between microcontrollers and some sensors and actuators. Thank you very much.